Am I audible?
Yes, sir.
And my screen is visible, right? My presentation is visible, right? Okay. So let's start the discussion. So we are in week 8 discussion for this course, deep learning, and this course was originally taken by Professor Sudarshan Iyengar, professor and head of the Department of Computer Science and Engineering of IIT Ropar, and myself Ayan Paul. I'm a PMRF research scholar from IIT Kharagpur, and I'm a PMRF TA for this course. My duties are I will practice you some questions so that it will be easier for you whenever you will be solving the assignments. Okay. And okay, someone is joining. Okay, so before this question answer session, what I will do is I will summarize some of the concepts that are discussed in the week, so that will be easier for us whenever we will be tackling the questions. Okay, so let's start the discussion. So this week, whatever we have done is we have seen a quick recap of this training of deep neural network. So how we train neural network? We train it by a algorithm known as backpropagation. Okay, so this is a small network, so we are training it by backpropagation. So training, what does training of the network means? Training of the network means we have to update the parameters that we are using in the network. What are the parameters that we use in the neural network? That are nothing but weight and bias. Okay, so training the deep neural network means we have to update the parameters. Okay, and we have to update the parameter in such a way so that we can minimize our loss function. Okay, so that is the concept. So this is a small network. You can see one input and one output, and inside we have one activation function, that is sigmoid activation function. So we can easily write our backpropagation algorithm. So we can update our weight by this formula. Weight equals to whatever our previous weight was minus eta of del w. Okay, del w is nothing but the gradient. And how gradient is calculated? Gradient is calculated by del L by del W. That means loss by change in loss by change in the weight. Okay, and by that you can easily update the weight. So this is for small network. Now let's just widen the network. How can we widen the network? We can widen the network by increasing the number of inputs. Okay, earlier we have only one input, now we have three inputs, so that is why this network is a wide network. Wide network, again, how we can train our network. We can train it by same algorithm, that is backpropagation. And earlier we were updating only one parameter, because here we have only one parameter. Now we have three parameter, w1, w2 and w3, so we will update by that way. Okay, so this is for widened network. Now how about deep network? Deep network means we have so many layers. Okay, earlier in small network or wide network we have only one layer. Okay, one layer or one hidden layer, whatever you can say. But in deep network we have so many layers in between. Okay, so that is a deep network. So this is the deep network. You can see we have the two hidden layer, and then we have a output layer. Okay, so that is the thing. Now here also, how we can train our network, same thing, that is back propagation. But here earlier, like as we have only one output and one weight, so we can easily calculate the gradient. Okay, that is del w1 and or del w whatever. But here, as our chain is our neurons are connected in different layers, so here what we have to do, we have to apply this chain rule. Okay, because you cannot calculate del L by del W1 directly. Okay, because from del L you have to somewhere like here, this is your loss function. So from loss function you have to come to output. From output you have to come to this input. Okay, this input or A3. Then you have to come to this weight. Then from this weight to this weight, and from this weight to this weight to H1, and then you can reach this A1. Okay, so A1, and from A1 you can reach this W1. So you have to follow a chain rule here. For calculating the gradient, you have to follow the chain rule in case of deep network. Now what about this wide and deep network both? Wide and deep network, again we have to do the same thing, that we have to follow the chain rule. But here the chain rule is bit more complicated, because again our network is widened. So this is a quick recap of how we can train the different type of neural network. So in all the neural network, what you have seen is, training neural network is a game of gradient. Okay, nothing we are doing. We are just in back propagation we have to subtract the gradient from our previous weight to get a new weight. So it is a game of gradient. Okay, the gradient has the responsibility of a parameter towards the loss, because we are calculating gradient by del L by del W. So that is why it always tells the responsibility of a parameter, that is W, with respect to the loss. Okay, so the gradient with respect to a parameter is proportional to the input of the parameter. Like the gradient is always proportional to the input. Okay, so that is another thing. So this is a quick recap of training of deep neural network. And more for more you can just revise our this week third lecture. In that I have discussed in detail how we can update the weights and bias parameters, so you can easily understand. Okay, so this is a quick recap of whatever we have learned so far. Is it clear to all of you? Okay. Okay. So now why we are recapping it, because definitely there are some limitation of this back propagation that we are using for training our deep neural network. What are that this is the original paper of the back propagation. You can search in the net, learning representation by back propagation errors. This is the original paper, and this was published in 1986. And whatever we have seen from 1986 to 2006 is 1986 only we got this back propagation, but up to 2006 it was not that popular. Why? Because when we used for a really deep network, it was not very successful. Typically, even after a large number of epochs, the loss did not converge, or the training did not converge. So what does this means is, what we want is, we want a loss value to converge. Okay, some parameter for which a loss is very close to zero. Okay, or approaching zero, that we want. But okay, someone is joining. Yeah. So I was telling, yeah, now what we want is our loss to converge to zero. Okay, zero or very close to zero, that we want, because we what we are doing is minimizing the loss, okay, for training the network. So that we want. But what we have seen from 1986 to 2006 is, in that period our neural network was not that popular. Okay, we got this algorithm known as backpropagation for training the neural network, but our neural network was not popular because the loss does not or training did not converge, or the loss does not approach to zero. So was the problem. So for dealing it after 2006, there are different strategy that we will discuss today, that will take care of this problem of back propagation that we faced till 2006. Okay, so that is our topic for today. So first thing is unsupervised pre-training. Okay, so what is this unsupervised pre-training is? See, yeah, this unsupervised pre-training, it was published by this Hinton and Salakutdinov, and in the year 2006. So what does this pre-training do is, see, we have a neural network like this. This is our network. Okay, so what we do here is, like we have done in the case of this autoencoders. Okay, we will follow the same strategy. What we will do is, we will take one layer, and we will try to understand the hidden representation by the next layer. Okay, by that what we will do is, we will get the, okay, by that what we will do is, we will get the weights of that layer. Okay, what I am telling is, see, there are two steps of this unsupervised pre-training. One is pre-training and there is fine tuning. So in first step, what we will do is, we will learn the weights. Okay, so earlier, if you will not do pre-training, like if you will only do back propagation, then you will initialize your weight. Okay, so what happens in initialization of our weight is, the training did not converge earlier. Okay, but now what we will do is, we will take one layer each, and we will see the next layer above the layer that we have taken. And then what we will do is, we will try to make an abstract of the first layer. Okay, abstract of the first layer. uh, the same principle that we have done in autoencoders. Remember, in autoencoders we have this input layer. Okay, we have this input layer, and we have this in between we have something called encoding layer, and we have this decoding layer. Okay, this is our autoencoder. So same principle we will follow. Now we have this neural network. Like see, in this network, we just focus on this box, means first two layers. Okay, so this is the input layer, and then you have this first hidden layer. Okay, so what we will do is, we will focus on this input layer and first hidden layer, and we will what we will do is, after this layer, we will be finding the output from this layer, and we will try that this hidden layer will learn the representation of this layer very well. Okay, so by that, what we are ultimately doing is, we are earlier we are just initializing the weight. Now we are not initializing the weight. Our algorithm will learn some weight by this phenomenon. So this is the unsupervised pre-training. Like see, in this diagram, we are just focusing on this two layer. What we have done, we have this red layer, then we are focusing on this first layer, that is h1. So first layer is x, and this layer is h1. Now we will be creating another layer, and we will try that this layer will learn whatever in this layer is by the help of this h1 layer. Okay, so x cap will learn whatever the representation of x is by the help of this h1 layer. Okay, and our objective is to minimize the loss function. Okay, if we minimize the loss function, then the weights associated with the layers that you are seeing, this weights will be learned. Okay, so this is unsupervised pre-training. Now why this is unsupervised pre-training and not supervised pre-training? Because here in this, we are not giving any labels. Like what we do in full training, whenever we are doing the full training, whatever we do is we give a layer in we give a label in this, okay, label in this as well as this input label as well as output label. But here we are not interested in any label, we are just interested in learning whatever our first layer is with the help of the next hidden layer, okay, to get an abstract of this layer. So this consider the deep neural network shown in the figure. So let us this focus X and H1. We will first train the weights between this two layer using an unsupervised objective. Okay, now again, why unsupervised? Because note that we are trying to reconstruct input X from the hidden representation H1. So again we are trying to reconstruct X by H1. So we refer to this as unsupervised objective because it does not input our Y level or X level. Okay, so that is why this is unsupervised pre-training. Okay, now next how we can proceed. Now what we do is we have learned this by H1. Now what we will do is we will learn this by H2. So same thing, we have learned this, so we have already learned this. Now we will be learning H1 layer by H2 layer, and then this is the H1 cap. That means this H1 layer will be learned by this H1 cap layer. Okay, so this is unsupervised pre-training. Now again our model will learn this H2 layer by this H1 layer by this help of H2 layer. And now again we have to minimize this loss function, that is this H1 from this H1 and H1 cap, the error between H1 and H1 cap, so that we have to minimize. Whenever we will be minimizing this, the weights associated with this layer will get optimized. So this is unsupervised pre-training. So this is the first step of unsupervised pre-training. The next step of unsupervised pre-training is something known as fine-tuning. So once you have learned all this layer, like this layer you have learned this, all these layers whenever you have learned, after that what we will do is, after this layer wise pre-training, we add the output layer and train the whole network using the task specific objective. Now we will give the label. Now we will not do the unsupervised pre-training. In fine-tuning process or the second step, what we will do is we will supply this supervised objective. That means we will supply the labels of this and we will supply the labels of this. So by this again our algorithm will learn. Okay, again our algorithm will learn the weights. Okay, note that in effect we have initialized the weights of network using the greedy unsupervised objective, and now we are fine tuning the weight with the supervised objective. So by this we will do the this process known as unsupervised pre-training. Okay, so this is the thing. Okay, so let me repeat again. So what we are doing in unsupervised, okay, so first thing, why we are interested in this unsupervised pre-training. So there are various limitation of backpropagation. The main limitation of backpropagation is we have seen from 1986 to 2006 that this backpropagation algorithm was not popular because training did not converge or loss did not approach to zero. So for this we have in 2006 we have come with this idea of unsupervised pre-training. What does unsupervised pre-training is? If we do not unsupervised pre-training, so we are initializing the weight by ourselves. Okay, so that is what we do before this unsupervised pre-training, and by that whatever we have seen, our training did not converge or loss did not approach to zero. Now what we are doing this unsupervised pre-training. So this unsupervised pre-training has two steps. One is pre-training, second is fine-tuning. So what we do in pre-training is, we have this network. In this network what we do is we are initializing the weight by ourselves, but we are adding a second step to it, that is we are doing this pre-training. What we do in pre-training is we take two layers one by one, so that second layer will help to learn the first weights between the first and second layer. Like this is your L1 and this is your L2. Okay, so what we will do is we will try that L2, by the help of L2 we will learn this L1 again. By doing this, what we are doing is earlier we are just initializing the weight, but now we are now our weights are not weights will get some sort of fine tuning. Okay, so that we will do as weight will get some set of fine tuning or modified. Okay, so that we are doing in this pre-training step. Then whatever we are doing this, yeah, why it is called unsupervised pre-training, because in this pre-training step what we are doing is we are not giving any label to the input as well as output. Whenever we are calculating the loss function in a supervised training, what we are doing is we are giving label to both input as well as output. But here in unsupervised pre-training we are not giving any labels to the input as well as output. We are just we just want to achieve this abstract of L1 by this layer L2. Okay, or we just want to we just want to learn the or learn the abstract of the previous layer with the next layer. Okay, that we are doing in pre-training step. Once our pre-training step gets over, what we are doing is we are giving a then giving the output layer. In pre-training we are not applying the output layer. We are just interested in hidden and this input layer. After this pre-training and fine-tuning process, we are installing this or we are putting this output layer, and then whatever we are doing a supervised learning. How we are doing the supervised learning? Now we are giving labels to both input as well as output, and by this supervised objective our weights will again get fine-tuned, and we will learn better. So we have seen that this pre-training, earlier the problem was that neural network did not converge, but with the help of pre-training we have seen our neural network is converging well. So this is the idea of this unsupervised pre-training. Now the question is why this unsupervised pre-training works. Okay, this is the thing. So two things can be there. One is better optimization and second is better regularization. So in optimization, this is our function, right? This is our optimization function or loss function. Okay, this function we have to optimize, that is minimize. Okay, so we have seen in the case of this neural network is we have this neural network surface is highly non-convex with so many hills and plateau. Like in the figure also you can see this is highly non-convex with so many you can see so many hills and plateaus. So earlier whenever we are not doing this unsupervised pre-training, we are initializing our weight in such a way that after so many epochs or so many iteration also we are not reaching the global minimum. So that was our problem. But now as we are doing this unsupervised pre-training, we are reaching the lowest point of loss. Okay, so that is better optimization. And again there was a study by La Rochelle et al. Rochelle et al is nothing but and others. Okay, this is a term we used in research, that if there are so many authors in a paper, we call it we just take the name of the first author and then call it et al, that means and others. So the study by La Rochelle and others show that if the last layer has large capacity, then L theta goes to 0 without even pre-training. So they have whatever they have done is they have in the last layer they have given so many neurons, and if they have given so many neurons in the last layer and tried without unsupervised pre-training, then for them also this loss converges to 0. Okay, but however if we have a small last layer is small or have a small capacity, then this unsupervised pre-training is very useful. So that is for better optimization. And the thing is better regularization. So at regularization we are doing the last two class of regularization only. So like regularization, what does regularization do is it limits the freedom of the weight. Earlier if we do not it limits the freedom of the weights. Earlier if we do not apply this regularization technique, our neural network or weights have the freedom to go anywhere. So what does regularization do is Earlier, if we do not do regularization, then our training loss reaches the zero, but same is not the case for testing loss. But what we do in the case of regularization, we restrict our training loss to reach to zero. Okay, so by that our model, whenever we are testing the model with different test example, our model perform better. Okay, that is the concept of regularization. Now by this unsupervised, yeah, earlier I have told you that we have lost L without regularization, but whenever we do regularization, we have this loss L dash, that is L plus something omega. Okay, L plus this omega theta. So in unsupervised learning, whatever the training we are doing in an unsupervised way, that will be comprising to this omega theta, and this L theta is our supervised loss. So we can explain the pre-training with the help of regularization also. So this is the concept. So is the unsupervised pre-training clear to all of you? Why we are doing it and why it perform better? Clear, right? So what are the two steps of unsupervised pre-training? One is pre-training, second is fine-tuning. In pre-training, we are doing this unsupervised process. In fine-tuning, we are doing this supervised process. Okay. So this is the thing about unsupervised pre-training. I hope it is clear to all of you. Okay. So we will move to the next thing, that is beta activation function. So another limitation can be our activation function was not so good in the from the year 1986 to 2006. So we will discuss, if we can better our activation function, then we can solve this limitation of the backpropagation. So beta activation function, so let's see activation function one by one and you will get the idea. So first is linear function. Okay, so in case of linear function, okay, this sigma is written, but this is not sigma, this is a symbol for this activation function only, and this activation function in this case is nothing but a linear function. So you can see by this equation also, so you will just linearly multiply w1 with the input, and you will get the pre-activation input of this first hidden neuron. And as we are doing the linear function, what does linear function mean is y equals to x. Okay, so whatever our pre-activation input will be there, that will be our post-activation input, or the output of the post-activation output, or the output of the neuron. Okay, so that means so this is the characteristics of our linear function. Okay, now what this linear function means is we will just learn the we will just learn the linear decision boundary. That means linear function can work whenever our point can be linearly separated by a line, like we have seen in the case of perceptron. Okay, perceptron or maculopates, whatever. So in all this, whatever we have seen is until our this data points can be linearly separated, then only we can use this linear function. So this is the limitation of this linear function. Like you see in this case, like in the diagram, we have two set of points, one is black set of points and one is red set of points. Now in with this linear function, it is impossible for you to draw a linear decision boundary and separate this red points with this black points. So this is the limitation of the linear function. So in particular, deep linear linear neural network cannot learn such decision boundary. Okay, but yeah, if we are using this in universal approximation theorem, then what we do is we just use so many layers, and we transform this linearity into non-linearity, and by that we can separate this data point. So this is just a note, you don't focus on it, just focus on the first point, that in particular deep linear neural network cannot solve such type of decision boundary in which the points are not linearly separated. So this was the limitation of this linear function. Then we came up with something called sigmoid function. So this is the curve for sigmoid function. sigmoid function, all the S type of function are known as sigmoid function. Okay, sigmoid function can be logistic also, tan h also. So whenever we are talking about sigmoid function, we generally focus on this logistic function only, not tan h function. Tan h function we say different, but we use the term tan h. But whenever you are using the term sigmoid, so always keep in mind that we are using using it for logistic function. So this is a graph for logistic function. It has this equation, sigma x equals to 1 by 1 plus e to the power minus x. Okay. Now this is the sigmoid function. You can see the curve. What are the characteristic of this curve is it always vary from or the range of this function is from 0 to 1. Okay, so it is always positive and the range of the function is from 0 to 1. Okay, and the thing is, as we are reaching higher values or higher values, then our sigmoid function converges, higher value as well as lower value, so our sigmoid function converges. So these are the two important characteristics of sigmoid function. So this is the derivative of the sigmoid function. Derivative is very important because whenever we are learning the neural network, we use this backpropagation, and for this backpropagation, this derivative is important. Now the thing is, there are some limitation of this sigmoid function also. What are the limitation is, see, when the derivative will be 0, the derivative will be 0 when the derivative will be 0 whenever whenever we are reaching a very high output, high pre-activation value of the neuron, or whenever we are reaching a very low pre-activation value of the neuron. What we will see is our gradient vanishes. Okay, so whenever this sigma a3 is whenever our sigma okay, when our gradient will vanish whenever our sigma a3 will be 1 or 0. Okay, whenever we will be reaching the extreme, that is 1 or 0, what we will see, just put 1 or 0 in this equation, our gradient vanishes. Okay, so this is known as vanishing gradient problem. Okay, so again I am repeating what is this vanishing gradient problem is. You know, the range of this sigmoid function is from 0 to 1. Okay, actually it is 0 to 1, not 0 to 1, it is 0 to 1. Okay, what I am telling is, it will not be 0 completely, or it will not be 1 completely, it will approach. Okay, so that is why this bracket will not be this square bracket, but this will be first bracket. Okay, so that is the thing. So whenever our value will approach to 0 or 1, our gradient will be 0. Gradient will be 0 means our weight will not get updated. So this is known as vanishing gradient problem. So this is the first problem of this sigmoid function. What is the second problem of this sigmoid function is, the second problem of the sigmoid function is, if you see this graph, what you will see is it is not zero centered. What we mean by zero centered is, whenever our value will be 0, the graph should pass with 0. But here, when our input is 0, our value is something 0.4 or 0.5, like that. So this is again a problem of this sigmoid function, that it is not zero center. Why it is a problem? Because whenever you will be doing the gradient will be dependent on the input, but the things in red, that will be either positive or either negative. Okay, so as it is not zero center, so it will be either positive or either negative. What does that means is, like this is the del w1 and this is the del w2. So whenever we have to reach from one point to another point, our weight cannot take this quadrant. Okay, this is the our weight can take this and this quadrant. That means this is the first quadrant and this is the third quadrant. The weight can only take the first quadrant and second quadrant. It cannot take this fourth quadrant or second quadrant. So this is again a problem of this sigmoid function, that it is not zero centered. So it will not like it cannot move. If you want your weight here, so it cannot move directly. Okay, so it has to move in this quadrant only and try to reach this here. Okay, it cannot freely move from this quadrant to this quadrant, it cannot freely move. So this is a problem, because now your training time will take a lot more time. If this is not the case, our training will happen very quickly, but as this is the case, our training will not happen that quickly. So this is again a problem of this sigmoid activation function. What is the third problem? The last problem, or the third problem of this, is it is computationally expensive. Like in this linear activation function, we are only doing a linear relationship, but now we have this logarithmic relationship or exponential relationship. So that is why it is computationally expensive. So this is about sigmoid function. Okay, so to deal with the sigmoid function, we have come with the new function known as tanh function. Tanh function again very similar to this sigmoid or logistic function. Actually this is not sigmoid, this is whatever we were discussing was logistic function. Sigmoid function is any S-shaped curve is known as sigmoid function. But this earlier whatever we are discussing, this is actually not sigmoid, this is logistic. Now we will be discussing about this tanh function. So this tanh function, it solve one of the limitation of this sigmoid function is it is zero centered. Now the range is between -1 to +1. Okay, so as the range is from -1 to +1, that means it is zero centered. So this is a advantage of this tanh function. The other two problem it cannot solve. It cannot solve the problem of vanishing gradient, because here also like when your x is 0, then this gradient vanishes. Okay, so this is also a problem for this tanh function. Also again it is computationally expensive. So this is the thing, but the main advantage here is we are solving the problem of this zero center problem. So this is about tanh function. Now we will move on to this next function known as relu function. So what is this relu function? So this is the equation of the relu function. That means whenever your output will be greater, whenever your input will be greater than 0, it will the function will give your output equals to input. But whenever your input will be negative, your function will give output to 0. So that is relu function. So next thing is it a non-linear function? Yes, it is a non-linear function, because now it is taking this both this thing, that is for negative for this negative input it is showing some different relationship, for positive input it is showing some different relationships. And also you can verify by writing this equation. This equation clearly shows that it is non-linear. It is again another type of relu function only. It is just modified relu function. So if you will write this again, you can see this, that it is a non-linear function. Now what is the other advantage of relu function? So unlike we have seen in case of this sigmoid or this tanh function, it does not saturate in the positive region. Negative region it is a different case, but in positive region it does not saturate. Like a linear function, it does not saturate in the positive range. Second, it is again computationally efficient, because we are not doing any exponential term. And third, in practice it converges much faster than our sigmoid and tanh function, because again it does not have this problem of zero centered and other things. So it zero center, also it is less computationally expensive, so that is why it converges faster. But the thing is, for relu function, the problem is in this region, that is in the negative region. In negative region it saturates to 0. So this is again a problem. So to deal with this, we have come out with this thing called as leaky relu. Okay, what does this leaky relu? Okay, there was another problem of this relu function is the problem of dead neuron. So what the problem of dead neuron is, if our bias, okay, this bias term is very negative. So what it will do is it will drive our input to negative term, and whenever it will drive our input to a negative term, our output will be 0, and we will face the problem of all this thing, that is vanishing gradient and other things. So that is known as dead relu problem. So two problem, or you can combine this two problem in one problem, that is we have this problem in the negative region. For positive region relu does not have any problem, but for the negative reason we have the problem with this relu. So for to deal with this, we have come with this leaky relu function. So unlike in relu, for the negative input we are getting our output as 0, but here for this negative output we are getting our output not equal to 0, some 0.01x like that. So by this we are solving the problem of one thing is this dead neuron problem, as well as this the function does not saturate in the negative region. So this is the benefit of leaky relu over this relu. Now there are two other function that researchers has came with. One is this exponential relu. So what does this exponential relu is? In the positive region, again same linearity, but in the negative region, in leaky relu we are applying another linear function in the negative region also, but here we are applying this
Exponential
exponential,
function.
exponential function. Okay. So it will have all benefit of relu, and if we want some benefit of sigmoid function, then we can use this function, like sigmoid function, it will better learn our representation, right? Instead of linear function, sigmoid function learns our representation better. So if we can, in the negative reason we can put an exponential function, then this type of function is known as exponential relu. And the one is max out neuron, that is just same thing like leaky relu only, but here we have different weights for this, or different slope for positive as well as negative part. That is why this is the slope, w1t is the slope and w2t is the slope. So we will have different weights for both the reasons. So that is max out neuron. So these are the summary of this is the summary of this. So first is sigmoid is bad, second is relu is more or less standard unit for the convolutional neural network. You can explore this leaky relu or max out relu, and then 10h sigmoid are still used in LSTM RA. This we will see later, but these are the three things. Sigmoid is bad because it has the problem of vanishing gradient, it is not zero centered, as well as it is expensive. Then we came out with this relu, but relu has this problem of the problem in the negative region, because in the negative region our neuron will be dead in case of relu. Then we can come up with this leaky relu, or even you can use this max out neuron. But max out neuron, the disadvantage is we are increasing the number of parameters, okay, because we are using two type of weights here, so we are increasing the number of parameters. So this is a problem of this max out neuron. So this is the summary of all this activation function. Okay, so is this clear to all of you up to this? Okay, nice. Then we will see the next thing, that is better initialization strategy. Initialization means we are initializing the parameter, that is weight as well as biases. Okay, so we will only see about weights here. So this is the better initialization strategy. You can say that this pre-training and supervised pre-training also fine tune our weight in the first process, but still what we are interested in, at the first step whenever we are initializing our weight, we have to better initialize our weight, that we have to look forward. Okay, so the intuition behind it is what will happen if we initialize all the weight to 0. So if we initialize all the weight to 0, then all neuron, the output of all the output or pre-activation of all the neuron will be 0 or same. And in this case what will happen is what will happen is all the neuron will display the same output. Okay, and this problem is known as symmetry breaking problem. Okay, this symmetry breaking problem is important to note, because whenever we will be assigning same weight to all the neurons, what will happen is it will not able to learn anything, because whenever our weight updation will happen, our weight updation will not happen well. If we initialize all the weight to equal value, or in fact the problematic is if we initialize all the weight to 0. Okay, so that is this problem is known as symmetry breaking problem. So for that we have to use different strategies. So solution of this symmetry breaking problem, so we have four cases. First is avoid initializing weights too close to 0, as we have seen, because whenever we will be initializing our values very close to 0, they may result in this vanishing gradient problem. Okay, so this is the thing. So that is why first thing you have to keep in mind is avoid initialize our weight very close to 0. Second thing is avoid initializing our weights too large, because whenever you will be initialize your weights very large, what will happen is whenever you are using this sigmoid function or any kind of tanh function or etc., what will happen is at the very higher input value, your curve will your activation curve will saturate. Okay, and whenever your activation curve saturate, we will have this vanishing gradient problem only. Okay, so that is again the problem. So two things you have to avoid. First, you have to avoid initializing your weight close to 0, and second, you have to avoid initializing your weight very large. Okay, so that two things you have to see. Next thing is yeah, you will be using weights for all your neuron, but from where you are taking the weight. So generally what we do is we take all the weights with some kind of distribution. So the distribution we generally use is a Gaussian distribution or the bell shaped curve. Okay, so we have seen it that whenever we are taking our weights, or whenever we are initializing our weight from this Gaussian distribution, if we are just using our weight as it is, then there are some problems. Okay, you can see your lecture notes. There are different derivation and etc. For this, but in short I am telling there will be some problems associated whenever you are using the weights taking completely from a Gaussian distribution. So for that, what you should do is you should normalize your weights. How you should normalize your weights? You should normalize your weights by this 1 by root n. That means whatever the weights you have, you just divide or scale the weights by this. Okay, scale the weights by 1 by root n. N is the number of input connection to the neuron. Whenever you will do your you will avoid this symmetry breaking problem. And fourth is this string, or this scaling the weight by 1 by root n, this string applies very well in case of sigmoid and tanh function. But whenever we use the same strategy in case of this relu and leaky relu activation function, then again we were facing some kind of problem. So to deal with that, whatever we are seeing in relu, like in relu, we have relu or leaky relu, we have two faces of this graph. One is positive phase and one is negative phase. As we have two faces of this graph in both relu and leaky relu, that is why what we will do is we will now scale by n by 2. Okay, earlier we are scaling by 1 by root n, but now we will scale our weights by 1 by root over n by 2. So whenever we are scaling the weight by 1 by root n, this is known as Xavier initialization, and whenever we are scaling our weights by 1 by root over n by 2, that is known as He initialization. Okay, so these are the four things that we have to see. So proper weight initialization is crucial for this break symmetry and ensure that neuron learn diverse feature. Okay, so why we want to do this or deal with this deal with this symmetry problem, or why we want to break this symmetry is to learn the diverse feature. So for that we should apply this 4 strategy. So again I am repeating, what are the 4 strategy? You should avoid initializing your weights close to 0. You should avoid initializing your weights too large, and if you are taking your weights from a Gaussian distribution, you have to scale by 1 by root n in case of this sigmoid or tanh function. What is the n? N is the number of input connection to the neuron. But this strategy or the third strategy does not work well with this relu and leaky relu function. Why it does not work with relu and leaky relu function? Because in relu and leaky relu you have two functions. Okay, one function is for negative part and the function was for positive part. Okay, so you have two functions. So that is why now we have to scale your weight by 1 by root over n by 2. So these are the 4 solution of your symmetry breaking problem. Okay, so this is the thing. So is it clear to all of you? Proofs and all you can refer to your lecture notes. Okay. Okay. So these are the 4 strategy you should always keep in mind. Now we are left with this last topic known as batch normalization. Okay. So you must have remembered that whenever we are doing that image problem, what we are doing is we are doing this normalization process. Okay. So earlier whatever we are doing is, what is this normalization process? We do this normalization process to have our input between 0 to 1. Why we do this normalization process? Because if some of our inputs are very large and some of our inputs are very small, then this large input and we are using our weights will be in a definite range. Okay, not very large or not very small, but our input can have different range. Like one kind of input can be very large, one set of input can be very small. Okay, so to deal with that, what we do is input normalization. Okay, someone is joining. Yeah, what we do is input normalization. Input normalization means what we are doing, we are restricting our input from 0 to 1, so that the large input does not have more influence on the updation rather than small input. So that is input normalization. But here what we will see is batch normalization. So what happens is whenever we are doing this activation we are applying this activation function, the neurons in the hidden layer, the distribution, it disturb the distribution many times because you are applying the activation function again and again. Okay, so the distribution, your data changes from your original distribution. Your original distribution can be Gaussian, but after applying this activation function, what happens is the distribution in the hidden layer, it disturbs abruptly. Okay, so to avoid this, what we do is a thing called batch normalization. So in batch normalization, what we will do, in input normalization we are only normalizing the input layer, but in batch normalization we will be focusing more on the pre-activation thing of the hidden layer. So that is the concept of this batch normalization. So it would help if the pre-activation at each layer were unit Gaussians. So what our target is? Our target is to convert the pre-activation into the unit Gaussians. Okay, so unit Gaussians, how we can do? We can do by this. We have to just subtract the mean and we have to divide it by root over variance. Okay, or just subtract the mean and divide it by standard deviation. Standard deviation is nothing but root over of your variance. So if you will do this, what you will ensure is that each neurons in the hidden activation layer are standardized, or it will give you the unit Gaussian value. So that we do in this batch normalization process. Like here you can see in the network, what we do at each layer, we are applying this batch normalization. After activation function, there can be a chance that our distribution will disturb. That is why we are applying this batch normalization again and again. Okay, now another thing, as we are applying or as we are converting our the inputs in the hidden layer to a Gaussian input, so is it it is always better if we can recover it. So what we will do, we have this recover formula. By this recover formula, SIK we have just calculated, that is the standardized pre-activation inputs of the hidden layer. Now what we will do, we will multiply it by we will scale it by a factor known as gamma k, and we will shift it by beta k. By this, what we will do, we will again recover our original or very close to our original pre-activation inputs. Okay, so this is the second step of this batch normalization. Now there are some difference between this input versus batch normalization. Purpose, it is standardized input feature before training. Yeah, whenever we are doing the input normalization, then it always focus before training, okay, not after training. So it is a pre-process step. Okay, but batch normalization, it is done within our training process to stabilize our training. So where it is applied, it is performed on the input data before feeding into the network. It is applied inside the network, typically after each layer, before or after activation. Okay, so this is the thing, we are applying this batch normalization typically when our network is training. Okay, so this is the difference between the input normalization and batch normalization. Computation is similar, like mean and standard deviation only we use. Effect on training, if we say, it is speed of convergence, but does not dynamically change during the training. Okay, because in whenever we are doing input normalization, then we are only consider with the input layer. Okay, so that will can only affect the weights associated with the input layer only, not the weights that are associated with the hidden layer. So that is why it can speed up convergence, but not dynamically. But here it is taking care of the distribution of the neurons in the hidden layer. So that is why that is how it affects on the training. Formula used are very similar. We are doing this minus mu by sigma, that is thing. Yeah, in this batch normalization, what we are doing, we are again transforming. Okay, whatever we are converting, we are again transforming by this two learnable parameter, gamma and beta. Okay, so this is another difference. Impact of back propagation affects initial weight distribution but does not impact gradients dynamically. Here it helps stabilizing the gradient throughout the training, making learning robust. So this is the thing about difference about input normalization and the batch normalization. Okay, so this is the thing. So is it clear to all of you? So by this we will be entering in our question answer session. Okay, so these are the topics on which our questions will be based: training deep neural network, unsupervised pre-training, beta activation, beta initialization strategies, and batch normalization. Okay, so this is the first question. Again, I will be requesting everyone to first guess the answer, and then we will discuss the solution. Okay, so we have observed that sigmoid neuron has become saturated. Okay, what might be the possible output value of this neuron? Option A 0.02, option B 0.5, option C 1, and option D 0.97. So any guesses for this? Am I audible?
Yes, 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 sir.
So any guesses?
One,
Yeah, what you are telling? 1. Okay, C you are telling. Any other option? Saturated. Okay, what does saturated means? Like this is,
maximum value.
yeah, maximum or minimum value, not maximum. See, this is the curve. Let me show you the curve, sigmoid function curve again. This is the tan h. Yeah, this is the curve, right? So where the saturation happens, this is also the reason of
One,
saturation, and this is also the reason of saturation. So there are two reasons of saturation. Okay, one, when the output is very
one,
close to 1, and another is when the output is very close to 0. So you
0.
have to see the option which are very close to 1 or very close to 0. So which are the option that are very close to 0 or very close to 1? Yeah,
A, C, D.
A, C, D. Okay, A, C, D. A, C and D. Okay, nice. So yeah, your guesses are almost right, but not completely right. Actually, the output, whenever we are talking about the possible output of a sigmoid neuron, it will be reaching 1, but it will not be equal to 1, like 1 by 1 plus e to the power minus x. Okay, its range is between 0 and 1. Okay, it will try to reach 0 or 1, but it will not completely reach 0 or 1. Okay, it will not completely reach 0 or 1. It can only reach 0 and 1 at minus infinity or plus infinity, and we all we all know that in minus infinity and plus infinity cannot be reached. So that is why option C cannot be the possible output, okay, of the sigmoid neuron. So option A and D are right. Okay, so option A and D are right. Okay, it will be very close to 0 or it will be close to 1. Okay, but not 1 or not 0, because 0 and 1 cannot be reached by our sigmoid neuron. So A as well as D is the correct answer. Okay, so is it clear to all of you?
Okay,
Why
sir.
not 1? Clear,
Yeah.
right? Yeah. So let's move on to the next question. Which of the following are the common issues caused by the saturating neuron in a deep network? Option A, vanishing gradient. Option B, slow convergence during training. Option C, overfitting, and option D, increased model complexity. So any guesses
A
for
and
this?
B, vanishing gradient, slow convergence during
Yeah,
training.
yeah. Not overfitting and increase model complexity, right? Yeah, overfitting,
Yes.
there is no issue of overfitting. And increase model complexity is always related to the number of parameters. Okay,
Hmm.
so number of which are common issues by saturating neuron. Here it is mentioned in saturating neuron. Okay, it does not give us more information about the number of parameters, etc. Okay,
Hmm.
yeah, it is a deep network, so can be the reason, but we are not sure about it. So saturating neuron, okay, yeah, saturating neuron, it will have this vanishing gradient problem. Whenever it will be close to 0 or even close to 1, what will happen is your weights will not get updated, and when your weights will not get updated, we will have this slow convergence during training. Okay, so this two are the right answer. Okay, overfitting and increased model complexity, we cannot say directly regarding this. Yes, it is a deep network, can happen, but this is not the question. We are only focused about saturating neurons. So that is why option A and option B are correct. Okay, so this is the thing. So is it clear to all of you?
Hmm. Yes, sir.
What are the challenges associated with using the tan H activation function? Option A, it is not zero center. Option B, computationally expensive. Option C, non-differentiable at 0. And option D, saturation. So what can be the option for this?
It is zero centered, therefore not A.
Yeah, it is not A, right? And what about option B? Computationally expensive. Yes, it can be
Yes,
computationally
yes.
expensive, because you know it is e to the power x plus e to the power minus x, I think, and e to the power x minus e to the power minus x, something like this. Okay, this is minus and this is plus. Okay, so I just, yeah, yeah, this is the formula of tan h function. Okay, e to the power x minus e to the power minus x, e to the power x plus e to the power minus x. So it is associated with exponential terms. So it is computationally expensive. That is true. Second, it is non differentiable at 0. That is not the case, because if you will see the curve does not is not flattened at any reason except at saturation. So at 0 it is definitely, yeah, it is passing with 0. Okay, just ignore my drawing, it will be passing with at 0. So at 0 it is not
Differentiable at 0.
differentiable, it is also incorrect. Saturation, yeah, saturation can be a
Saturation is there.
problem at this high value, as well as whenever it will be approaching to approaching at a high value, it will be -1 to +1. So that is why saturation can be a problem. Whenever it will be uh, -1, sorry, +1, the saturation is always a problem. Okay, because you can see the differentiation. Okay, I think I have included differentiation here also. Yeah, this is the derivative, right? So whenever it will be it will be reaching 1. Okay, this region, whenever it will be reaching this region, there will be a problem of saturation, and there will be a problem of this vanishing gradient problem. Okay, so option B as well as option D is the correct answer. Okay, so is it clear to all of you?
Yes, sir. Yes, sir.
Clear, right? Okay. So question number 4, given a neuron initialized with weight W1 equals to 1.5, W2 equals to 0.5, input X1 equals to 0.2, X2 equals to minus 0.5, calculate the output of the relu neuron. Yeah. So how you can calculate the output of a relu neuron? Okay, so any neuron, how you can calculate the weight? Sorry, how you can calculate the output? There are two input. Okay, x1 here, and there is x2 here, and there are two weights, w1 here and w2 here. Okay, and a neuron has two part. Okay, half of the part, the below half is known as pre-activation part of the neuron, and then we have post-activation part. So post-activation part will be your output, pre-activation is your input to the neuron. Okay, so how pre-activation can be calculated? That is x1 w1 plus x2 w2, right? x2 w2. So what is x1 w1? x1 w1 is x1 w1, yeah, x1 0.2 into 0.2 into 1.5, right? 0.2 into 1.5 plus this thing. What x2 is? What x2 is minus. Okay, so this is minus minus 0.5 into 0.5, right? 0.5 into 0.5. So this is your input to the pre-activation part of the neuron. Okay, that is this is 0.30 and this is 0.25. So your answer will be 0.05. Okay, so this is up to pre-activation part. Then we have to apply our activation function. So what is our activation function? Activation function is a relu. So what does relu do is relu will be fx equals to we have to maximize. Okay, maximize 0
0, comma x.
0 comma x. Okay, so what does our x is? X is
0.5.
0.05. Okay, so maximize 0 and 0.05, so our answer will be
0.05.
0.05. Okay,
Right.
so 0.05 will be our answer. So is it clear to all of you?
Yes, yes.
Any doubt regarding this?
No, 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 no,
Okay,
no,
so
no.
let me show you the solution also. It will be step by step in case someone don't understand it, so it will be better for him. Okay, so this is the solution. So that only I have told you. So we have to calculate the pre-activation thing, that is 0.05. Then we have to apply this relu function, that is max 0 and z or x, whatever you tell, and whenever you will do it, your answer will be coming 0.05. So this is I think integer type question. Yeah, it is this question. So 0.05 is your answer. Okay. So question 0.05 is your final answer. Okay. So let's move on to the next question. So how does pre-training prevent overfitting in a deep network? Option A, it adds regularization. Option B, it initializes the weights near local minima. Option C, it constrains the weight to a certain region. Option D, eliminates the need for fine tuning. So any guesses for this? Any guesses for this? Okay, so let's analyze this one by one. So pre-training prevents overfitting. So yeah, definitely it will add regularization. I have shown you it does both the thing, that is regularization also and optimization also. Better activation, better optimization, better regularization. Okay, does this thing, yeah, here. So why does unsupervised pre-training work? It does this better optimization and it does this better regularization. So whatever you are doing in the unsupervised step, that is better regularization only. Okay, so that is the thing. Okay, so let's move on to question. Yeah. Yeah, so it adds regularization. So option A is right. Option B, it initializes the weight near the local minima. Yeah, it initializes our weight to the local minima. This is not correct. Okay, initialization, we have to do initialization for with ourselves only. But what it will do is it will constrain the weight to a certain reason, because whenever you are doing the first step, that is pre-activation, what we are doing is we are landing the uh, better abstract representation of a hidden layer of the or the input layer. Okay, so by doing this, what we are doing is we are constraining the weight to a certain reason. Earlier we are initializing our weight and then we are doing the fine tuning process, so our model was not converging. But in this approach, what we are doing, we are doing a step known as unsupervised pre-training. So during this unsupervised pre-training, we are ensuring that our weights constrained to a certain reason. So that is why option C is right. Option D, it eliminates the need for fine tuning. Option D is again not correct, because in unsupervised pre-training there are two steps. First is this pre-training, second is this fine tuning. So we have to do the fine tuning, because fine tuning only we will utilize our supervised objective, that is our objective of the neural network. So that is important. So that is why option D is also wrong. We have to do the fine tuning. So option A
Internet.
as well as option C is the correct answer. Okay, option A as well as option C is the correct answer. So any doubt regarding this?
No, sir.
Okay. Okay. Okay, so let's move on to the next question. We train a feed forward network and notice that all the weights for a particular neuron are equal. Okay, what could be the possible causes of this issue? Option A, weights were initialized randomly. Option B, were initialized to a high value. Option C, weights were initialized to equal values. Option D, weights were initialized to 0. So any guesses for this?
Weights were initialized to equal value.
Yeah, equal value, and also it can be weights initialized to 0 also. Okay, because
Okay.
whenever you will be initializing our weights to 0, what will happen is this back propagation will not work, because there will be no updation of weights. Okay, so this is the thing. Whenever weights are initialized to 0, if all the weights neuron are initialized to the same value, they will update in the same way during back propagation, maintaining the equality through the training, and this leads to this symmetry. And second thing is weights were initialized to 0. Whenever the weights were initialized to 0, they will remain equal after each update, preventing meaningful learning. So this two are the problems. Okay, weights, whenever your weights are initialized to a higher value, so it can cause saturation, but it do not necessarily ensure that all the weights will be equal, because here it has been told that all the weights of the neuron equal. So during this high value initialization, there can be a problem of vanishing gradient, but this do not necessarily ensure that your weights will be all your weights will be equal. So this is the problem with this statement. So that is why option B is wrong. If we are just randomly initializing, then definitely it will not get equal values. Okay, the weights will not get equal values. So option A is also wrong. So that is why option C as well as option D is right. Okay, so option C as well as option D is right. Okay, so this is the thing. So is it clear to all of you?
Yes.
Okay. Now let's move on to the next question. Which of the following is true about the role of unsupervised pre-training and deep learning. Option A, it is used to replace the need for labeled data. Option B, it is used to initialize the weights of a deep neural network. Option C, it is used to fine tune a pre-trained model. Option D, it is only useful for small data set. So any guesses for this?
No, 1 and 2, A and B.
It is used to replace the need for labeled data. No, this is not correct, because label data we have to give. Our objective is supervised, not unsupervised. Unsupervised, we are only doing the pre-training. For this we are only doing we are only utilizing the unsupervised part in only this pre-training. There are two steps. One is pre-training step, second
Pre-training
is
and
fine
fine
tuning.
tuning. Fine
Fine
tuning.
tuning, we are utilizing the supervised learning. Okay, supervised
Learning. Yeah,
learning
yeah.
means labeled data. So that is why option A is not correct. Option B, it is used to initialize the weights of a deep neural network.
Yeah, that's true.
Somewhat can be correct. Okay. Option C, it is used to fine tune a pre-trained
No,
model. It is used to tune a pre-trained model. So if a
it's
pre-trained
supervised
model
learning.
is given to you, so this is not the objective. Again, this is
Yeah,
wrong. Yeah.
supervised training. Yes.
So option D, it is only used for small data set. Again,
Wrong.
this is wrong. So option B is the appropriate
B is the
option.
correct answer. Okay.
Option B is the appropriate option. That is, it is used to initialize the weight of a deep neural network, because whenever we are doing the unsupervised pre-training, we are constraining the weight to a certain reason. So that is why this can be correct, that it is used to initialize the weight of a deep neural network. So that is the thing. So option B is the only correct answer. Okay, someone is joining. Okay, so let's move on to the next question. Which of the following is an advantage of a unsupervised pre-training in a deep learning? Okay, so it has been reduced in overfitting. Pre-trained models converges faster. It improves the accuracy of a model. It requires fewer computational resources. So any guesses for this?
Pre-trained model converges faster.
Yeah, exactly. So this is one of the limitation of backpropagation. That is why we are using this unsupervised pre-training. So pre-trained model converge faster. It has in reducing overfitting. Yeah, it does some kind of regularization. We can say option A can be right. Let's see. It improves the accuracy of the model. Accuracy, see again, if option A is right, option C is also right, because it will then perform well on the test dataset, and it requires fewer computational resources. No, option D is completely wrong, because unsupervised, we are adding another step, that is unsupervised pre-training. So we are utilizing more computational resources. Option D is wrong. So I think A, B, C are the correct option. So yeah, so it reduces overfitting because we are doing this regularization step. Okay, so that is why we are helping in reducing overfitting. Pre-trained model converges faster, that we all know, improves the accuracy of the model. Yeah, so option A is correct. So option C should be more or less correct. Okay, because again it will perform well on the test data set, and that is why option C is correct. Option D is wrong, because we are
Then I have
adding
a doubt.
this. Yeah.
Sir, in the fourth, it requires fair competition resources. But actually, when we do unsupervised pre-training, then we tune the weights. Then when compared to a training where we don't have pre-training, but will it not make more time to converge to this weight? For example, I say we have a model with unsupervised pre-training and fine-tuning, and we have another neural network which has achieved the same weights, but which has not undergone unsupervised pre-training and fine tuning. Therefore, when you compare the both, the second one might have taken more time or computing time than the first one. Am I right? Because it does not, because our unsupervised pre-training has fine tuned the weight has
Yeah,
been
yeah. It
come to
constrained.
the
It already constrained the weight to a certain reason by
certain
this
level, then
pre
quickly it
training.
has done. So
Yeah,
that's
yeah,
why the fourth question is
No,
tricky
but if
because
you will compare with the natural model, like without this unsupervised pre-training, because in fine tuning you have to follow the step again. Okay, whatever the derivative you have to do, you have to do again. Okay, so that there is
yeah.
no shortcut. Like you can escape one of the derivative that you cannot do, because in fine tuning again you have to fine tune all the way. Okay,
No,
so
no, but
there
that
are
is
two
okay, sir.
steps.
But
Yeah,
I'm completely accepting that.
yeah.
But what I'm saying is the same weights. If you take a model two model, one has gone through unsupervised pre-training and fine tuning. The second model has reached the same weights, but it has not gone through unsupervised pre-training, but straight away the training of using weights backpropagation algorithm. But they both have achieved the same weights. So if you compare both that way, the second one might have taken more time because this unsupervised pre-training has constrains the weights to a particular level. Then fine tuning has improved it, but this has to
but
go
but
achieve that
when
weight.
but yeah, but when it was constraining to to a particular weights, in that process it is taking that time, no? That
No,
process it
no,
will
but
take
the
the time.
second one, it takes more time now because it has to come to that weight. It will, already we have limited that search space. Then the only we are fine tuning. But
Yeah,
this
limited the search
this way
space
it
as
takes.
well, but in the first step also we are doing the process of auto encoder only, right, for each layer. So it is if it is a very deep network, so it has to do the process of this auto encoding for each layer, right? So that takes a lot of time. And also if you have a this case of this large model, and large model means a deep model as well as more data set, so this pre-training will take a lot more time, because we have to do the process of training, unsupervised training for each layer one by one, or two layer at
Uh-huh.
once. For that it will take a very
Okay,
much
okay,
more
okay,
time.
okay, okay, okay,
So
okay,
this is
okay.
the
Understood.
this
No,
can be
understood.
the explanation. Okay,
Okay, thank you, please.
now let's move on to the question number 9. What is the main cause of this dead relu problem in deep learning? Option A, high variance. Option B, high negative bias. Option C, overfitting. Option D, underfitting. So any guesses for this? Yes, Shruti is telling D. D. Okay, underfitting. Okay, no, underfitting is not the correct answer. Neither overfitting, underfitting. These are all related to number of parameters. Okay, dead relu problem. What is dead relu problem? What is the relu? Relu is fx equals to maximum of 0 comma x.
Zero
Okay,
comma x.
maximum of 0 comma x. Okay, when the neuron will be dead, the neuron will be dead when its output will be 0. So when the output will be 0, when your input will be so much negative, high variance. High variance also you cannot say high variance.
Negative bias.
Yeah, high
No.
negative bias, because what you are doing in neural network, you are doing wtx plus p. Okay, whenever you are achieving the or want to calculate the pre-activation input of the neuron, you are doing this wtx plus b. Now if this bias is highly negative, what it will do is it will always give a negative pre-activation input of the neuron. And when it will give a negative pre-activation input to the neuron, your answer will be 0, or it will be a dead relu problem. So option B is your correct answer. Okay, so high negative bias. So this is the thing, whenever your B will be very much negative, so your this means output will be 0, and it will be a problem of this dead relu problem. High variance, overfitting, underfitting, this you cannot say anything regarding this dead relu problem. Okay, so this is the thing.
Sir, high variance is what it means actually. I didn't understand that. Overfitting and underfitting is okay. But what it means, high variance means like the uh, variation in what input or training pattern.
Variance is related to whenever you are sampling your data in different test set, and you are making this model again and again. High variance means
Okay,
your
okay.
graph will be like, yeah, like this is the function
Original
whenever you
data.
are doing with test1 t1 dataset. Your t2 will be very much far away, like your t2 can be somewhat like this. Okay, so that this is high variance problem. If your variance is small, then this t2 will be very much
Merging with
closer
the
to this or merging with
T1.
this t1, so that is low variance.
No,
So there
understood.
is no how we can say that it is a high variance or something.
Ah,
So that is why we cannot say
mm.
something like that. So this option B is the right answer. Option A, C and D, I don't think that we can explain anything with this dead relu problem. Okay, so this is the thing. Option B is the correct answer. So is it clear to all of you? Oh. Now let's move on to the next and last question. What is the main cause of symmetry breaking problem and deep learning? Okay, so option A is high variance, option B high bias, option C overfitting, option D equal initialization of weight. So this should be clear to all of you. So I want everyone to guess the answer. This we have discussed many times. So why the symmetry breaking problem occur? Symmetry breaking problem occur because of this equal initialization of weights. Okay, other three are I don't know again. This does not make sense to the symmetry breaking problem. So what is the symmetry breaking problem is whenever you will give equal weights to your neuron, your neuron will be they receive identical gradient during back propagation, and it will update in the same way, and it will not able to learn the features. Okay, different feature that needed to be learned by this neural network. So this is the symmetry breaking problem. So that occurs when you do equal initialization of weights. Option D is the right answer. Okay, so this is the thing. So I hope it is, yeah. Steven, any doubt?
No, sir. No, no.
Okay. Okay. Okay, so by this we have ended this question answer session. Okay, and again I have given some of the codes to you in the DL code folder. Okay, so let me again show you also. So is this the DL code? Yeah. Yeah, so is that thing? Yeah. So is my screen visible to all of you? Am I audible?
Yes, sir.
Yeah. So this is the DL code folder. Okay, you all know this folder, and in this folder at the top you will find this DL code, and you can see some of the codes here, like beta activation. This is, yeah, batch normalization. This code you can open, as well as this thing, that is, what is the pre-activation, beta read, and so yeah, this unsupervised pre-training, as well as this batch normalization. You can see this is the code for batch normalization. Okay, and this I have taken that your MNIST dataset, and I have also included all of these definitions and formula here for the easiness. And in neural network in Python, you need not to do the batch normalization for each layer by calculation or by any function. You just have to put this code, that is batch normalization, in a layer. You have to just put this batch normalization function. That is a pre-Python code, and just by writing this, you can do this batch normalization. and I have compared the training without batch normalization as well as training with batch normalization, and this is the comparison. Okay, comparison, you can see the loss whenever we are doing without batch normalization, then this is our loss. Okay, we are getting our loss after this 10 epochs as 0.09, but whenever we are doing this batch normalization, see the decrease in the loss. Okay, we are getting our loss as 0.06. So batch normalization, what it does is it converges our loss to a lower value. That is what we are interested in. Okay, so this is the code for batch normalization. You can just use this code, just copy the code to your drive, and you can why this thing is hanging. Okay, you can just copy the code to your drive. There will be something written copy to drive, and you can just run this code and you can get the results. Also, you can try with different dataset. I have tried with this MNIST dataset. You can try with different type of dataset, like one dataset is your Oliver something dataset, in which you will get the phase dataset, etc. You can try with different type of dataset. So this is the thing about batch normalization, and this is about unsupervised pre-training. Unsupervised pre-training also I have shown some of the codes. Okay, so this is supervised pre-training. Okay, and training the base model without pre-training. So this is the thing, and again you can see the difference in this losses, etc. for this loss comparison for this baseline model as well as your pre-trained model. Okay, so this codes you can see, you can just copy to your drive and you can just run the codes by your own. Okay, and other codes also I have given you all the codes like this. You can see this different for, yeah, not this better activation function, this better weight initialization strategies, etc. Also you can open the codes and see the results. Okay, or you can just copy the code and run for seeing the results. Okay, so this is the thing. Okay, so is it clear to all of you where to find the codes? So is there anyone in this meeting who don't know where the codes, etc. are available? Codes or lecture content are available. Is there anyone still who don't know where the codes are available? Because this is important. I am just writing the codes and no one is seeing, so that does not make sense. So that is why I am asking, is there anyone in the meeting who don't know where you can get the codes or you can get the lectures? Everyone know, right? Okay. Okay, so by this I am ending the session for today. Okay, so bye, we will meet on the next Tuesday.
Thank you, sir.
Okay.
Thank you. Thank you, sir.